I will begin. Just a second here. So let me begin with a word of prayer. Oh, thanks. Dear Heavenly Father, we thank you again for this opportunity we have just to study your creation. Just pray you help us use this time wisely, and I just pray that we'll be able to understand the homework solutions that we go over today, Lord. In your name we pray. Amen. All right, so I'm just going to try to go through these pretty quickly, unless there's something that you want me to talk about more. So this problem was to show that problem 37, this is the first problem after test 1, right? It's been a little bit since you looked at this one at this point, but here it is. So you got a homomorphism from a group 1 to a group 2. It's supposed to prove that the kernel is a subgroup of G1 and the image of the homomorphism is a subgroup of G2. So basically what I do is, the identity maps to identity, so the kernel's non-empty. I pick A and B in the kernel, and I look at the image of AB inverse. Well, that's the image of A times the image of B inverse, because we proved that for a homomorphism, we have phi of A to the n is phi of A to the n. Right? We proved that before this point in the course, so I'm using that now. And but of course, that's the identity again. So therefore, if A and B are in the kernel, then AB inverse is in the kernel. Therefore, by the one-step subgroup test, we have a subgroup. People don't usually have too much trouble with that one. Let's see here, 2. To show that the image is a subgroup, notice that it's non-empty because the identity maps to the identity, right? So the identity is in the image. And if I pick A and B in the image, that means that there are some x and y in the domain which map to those, right? And so if I look at AB inverse, that's phi of x, phi of y inverse, which is phi of x, phi of y inverse, which is phi of x, y inverse because of the homomorphism property of phi. And that then says that this AB inverse is mapped to, under phi, by x, y inverse, which of course is an element of G1 again, because G is a group. So if I multiply x times y inverse, something in the group times something in the group, but then the group again, consequently, that shows that AB inverse is reached by the image of that element. Consequently, AB inverse is in the image of the homomorphism. Consequently, by the one-step subgroup test, the image of phi is a subgroup of G2. My proposition 2.18 actually does this for an arbitrary subgroup of the domain and an arbitrary subgroup of the codomain. So we actually have a general, this is a special case of a theorem I prove in the notes. In particular, the kernel is the inverse image of the identity in the codomain, whereas the image is the, it's the it's the image under the homomorphism of G1. Okay. So technically speaking, at that point, you guys could have looked at the notes and made your life easier. I doubt anybody was really at that level of thinking when they did this problem, but that's fine. Galilean number 5 on page 130. Show U8 is isomorphic to U12. Man, I wish when people ask me questions about this, I was already where I needed to be in my thinking. I would have told them most clearly, you can write down a Cayley table for one, write down the Cayley table for the other, state the isomorphism, and then say that the Cayley table having the same pattern proves that the isomorphism is in fact an isomorphism. Yeah, I think that is about the most efficient way to communicate a finite set of specific relations, and for an infinite group that won't work. But for this, that's a pretty good thing. I mean, and of course there is something to that. You have to put the numbers in the same arrangement in order to make the pattern match up. That doesn't always happen for you. Sometimes you need to take a group and you need to reorder the elements in order to see the pattern matching explicitly, But there's nothing, it just so happens that put in their natural order, they match up. And you can clearly see that the isomorphism identity 1 to 1, 3 goes to 5, 5 goes to 7, 7 goes to 11. That gives us an isomorphism from U8 to U12. And
in finding an isomorphism, you want to make sure generators match up and identities match up.
Right. Send generators to generators. If we're thinking about constructing it, right? Now, because I wrote this solution, because I was very, what's the word, behind, by the time I wrote the solution, I'd already covered some other things.
Right.
So I would point out that we can now see U8 is Z2 cross Z2. These are both, and likewise U12 is also by the, it's U3 cross U4, but that's U2, Z2 cross Z2. In other words, these are both isomorphic to the Klein 4 group. So, as I say, from the future. All right, 39. Prove S4 is not isomorphic to D12. There are many ways to prove not isomorphic. First of all, first thing I always try is the order. If the order doesn't match, if one is infinite and one is finite, game over, they're not isomorphic. You can't have a bijection from an infinite set to a finite set, right? So that's one thing. Or you can't have a bijection from a finite set to another finite set of different cardinality, of different size, right? So that's always something to look for. That's no help here, though. Then I start looking at order of elements, and that turns out to work for me because in D12, in our study of dihedral groups, we've figured out that all of the reflections have order 2. This is something we know from our previous work. And we also know that the rotation by 180 degrees has order 2, which is x to the 6th in D12. So there are 1, 2, 3, 4, 5, 6, I can't count, 12, 13 elements of order 2. But in S4, there are just these 6 transpositions, and them's the only elements of order 2. So as you can see, 13 and 6 are different, and consequently, if there was an isomorphism, you'd be able to map the 13 elements of order 2 in D12 to 13 elements of order 2 in S4, but that's preposterous because there aren't 13 distinct elements of order 2 in S4 to map to. So these can't be isomorphic because isomorphisms preserve the order of elements. So yeah. Ha! I did assign this problem. Lorenzo was asking me earlier if I had mentioned in the notes that I assigned this problem, and then she was debating whether or not I actually assigned it. So I think what we have figured out is that said student didn't do said problem, which is okay. I know.
I think I didn't understand it at the time.
Yeah. This one's fun. So here we have the group defined by linear combinations of rational numbers and rational numbers times the square root of 2. And then we've got these particular quirky 2x2 matrices, again with rational entries, AA, 2B, we're supposed to show that G and H are both additive groups, all right? And we're also supposed to prove that G and H are closed under multiplication. And we're also asked if psi, the isomorphism from 1 preserves the multiplication, all right? So first of all, I have to invent an isomorphism. It was suggested to me by these letters. So psi of A plus B root 2 is A 2B, B, A. Admittedly, there's a giant leap right there, but that's the creative leap of defining an isomorphism. Right? Short of having a Cayley table to match a pattern, for infinite groups, you just have to kind of grab onto something about the group that you want to match up. So I don't know. I don't have a good explanation for why I wrote this down, except that I couldn't think of anything else to do. So I mean, exactly. Try it, see if it works. Believe in the kindness of Galen that he wouldn't write these letters down, and then the isomorphism actually requires you to put like A over 2 minus B, and over here B plus 7, and this one is B plus 8. No, I mean that's not I know some people who might do that. I won't name names. I try not to be. If I do that, it's an accident. I mean, it's on purpose for your learning. Let's see here. So no. Anyway, so you add. We can add, and then yeah. Okay, so it's additive, and it's clearly a bijection because if I pick this point, I can map to it, right? So it's obviously onto, and the kernel is clearly 0. So it's a bijection. So it's an additive bijection. It's a homomorphism of the additive groups.
Can you remind me how showing the kernel equals zeros shows it's one?
Well, that was a theorem we proved. If we have a homomorphism and the kernel is 0, or the identity, then it's a one-to-one map.
Oh, if it's the identity. And
Right.
0 is that.
Yeah, 0 is the identity here. Yeah. Indeed, if it was a multiplicative group, then we would be looking for 1, or the identity matrix, or the identity transformation for a group of composition, or just E in the abstract, you know. But yeah, if the kernel has just one thing in it, and it's the kernel always has at least one thing in it, because the kernel is a subgroup, as we proved earlier in this homework. And so isomorphism is just a special kind of homomorphism. So yeah. Anyway, so that proves that psi is a bijection, and it's a homomorphism. Consequently, it's an isomorphism. And then multiplication here. So you multiply like so. Square root of 2 times square root of 2 is 2. We know this. So what? Well, this is again a rational number plus a rational number times root 2, so it's closed under multiplication. In fact, this set, rationals plus square root of 2 times a rational, square root of 2 times the rationals is an example of a ring. It's closed under addition and multiplication, where the multiplication distributes. We don't know that yet, but, well, actually I stated it the first day, didn't I? But we don't know it yet. Let's see here. We'll get back to it though, don't worry.
That's mostly for 22, isn't it?
Nope. I didn't say ring by spring. I said ring by October 21st.
Nice.
Wait a minute, 31st.
I was going to say 21st. That's
Yeah.
before this test.
Yeah, but it's in October. The rings are upon us very soon. Once we get past that little, class participation exercise next Wednesday. Yeah. So, indeed, it's closed under multiplication. And let's see here. I said you could go further and prove that if you remove 0, then every element has a multiplicative inverse, in fact. All right, but I'm moving along here. So if we look at a 2b, ba, x, 2y, yx, and h, multiply them, I get this. But if you look at that, that is what? I mean, that's, again, an h, right? So h is closed under matrix multiplication. Because, again, it's this number, and then this number again, this number, twice that number. So rationals all around. And then you can check the homomorphism property with respect to the multiplication. Although, again, maybe I shouldn't say that yet because we haven't proved that everything has an inverse. I haven't proved that it's a multiplicative group. I'm just claiming it is, but it is, as long as you remove 0 from it. That's what I was saying up here. So multiplying gives me this, which gives me that, which when you unmultiply this gives you that, which by the way is psi of this times psi of that. So yes, the isomorphism, the natural isomorphism that I invented, that I stole from Galilean by just a pattern of notation in the problem, in fact, is also multiplicative in this sense. Psi of a product is a product of the size, yeah. So there's a close cousin to this problem, the similar isomorphism between the complex numbers, which is kind of like, real number plus square root of -1 times the real numbers. And particular 2x2 matrices is a follow-up problem in this, this part of Galilean. Did you have any questions? What I'm doing is I'm just going back to the homework that, I'm just, so right now we just got through 10. 11? No, is this 10?
That was 10.
Oh, this is 10. I can't count. All right. So, do you have any questions about this one? I can go back. Is this problem the S4 not isomorphic to D12? Now, this one I talked about too, problem 38. The main thing I said here was that, when we have an isomorphism of small groups, use the Cayley table. Yeah, I think I told you that already. I wish I'd told that to you when you asked me about it. that day. It didn't click for me until like a day after. And I had already wasted tons of my own time, if it's any consolation, writing things inefficiently. But, you know, this is the learning. All right. So 11. All right, so show that the inner automorphisms of G is a subgroup of the automorphisms of G. So context here, this is a subgroup of the permutations of G. Permutations of G being bijections of G. Automorphisms of G are bijections which are also homomorphisms of G to itself. So it's more than just being a one-to-one map. These things are also operation preserving with respect to the multiplication of G. So that's a little bit more structure. It's a lot more structure. Let's see here. Anyway, so the inner automorphisms are those which are conjugation maps. All right. So, I mean, you could think of them as the group action, right, nowadays. So there's the group action by conjugation in our current talking. So, but on the other hand, the automorphism, again, is just f from G to G, such that f is an isomorphism. With respect to function composition, this forms a group. That has been proved elsewhere. So we just need to show that this forms a subgroup of that guy, all right? It's a separate homework problem to prove that the automorphisms form a group. Anyway, so first of all, the conjugation by the identity map is the identity map. Okay, different identities. Like this is the identity function from G to G, whereas this is the identity element in G. So don't lose track of your identity. We don't go for that here. Oh no, was that a microaggression? I don't know. This may not be a safe space anymore. I think it's safe for you guys. Let's see here. Let's see here.
Just so long as we don't start
Yeah.
crazy or something.
Yeah. Let's see here. Thus, the inner automorphisms of G contain the identity and. Sorry, I've my energy has. Just a second. I gotta find some reserve power. Okay, so the inner automorphism is non-empty because I've just shown that the identity map is an inner automorphism, right? So now it's a subset, right? It's clear it's actually it's not clear that it's a subset. We need to show it's a subset, all right? So, I mean, a lot of examples we've worked with subgroup tests, it's kind of like, duh, it's a subset. But here's one where actually some proof is required. Not a lot, but if I look at the inner automorphism acting on a product, it's this. But then if you use your imagination, there's a G inverse G in the middle, which is this. So consequently, it's a homomorphism. And I still need to show that it's a bijection. So the kernel, which is X that maps to the identity, well, I can solve this for X basically. So the kernel is the identity, which shows it's injective. To see it's surjective, pick any element you like in G, let's say H, and notice that if you conjugate by G inverse, then that's H, which shows that it's surjective because I picked an arbitrary point in H and I mapped to, and from this image, from this point in the domain to H again. So H is B sub G, the conjugation by G map is surjective, is what this shows, right? So if G is onto. Incidentally, this also happens to show you that conjugation by the inverse is the inverse of phi G, which is something I prove again later in the solution. But you know, if I was lazier, I could say, hey, by the way, this is phi of G inverse, right? So this shows that phi G composed with phi G inverse is H, right? Okay. Anyway, brevity is the soul of wit, and you can tell from my solutions where I fit in. So we have shown that this is an isomorphism because it's a homomorphism, which is bijection. Consequently, conjugation by G is an automorphism of G. All right, now we've got that it's a subset. Now we got to check the one-step or two-step subgroup test. I will use two-step, I think. So phi G and phi H in inner automorphisms of G. I love that it's phi G. Sorry. Oh yeah?
In the middle of the night, in the middle of a coup.
Oh really? In the middle of a coup. I once landed in the Dominican Republic with plane troubles, and I was with a plane load of Haitians. And they would not let us get off the plane because I don't know if you know how Dominicans feel about Haitians, but well, you know, it's yeah. It is amazing. Like you can see the border. Like you go from like this decimated wasteland, deforested, whatever, to just baseball field after baseball field after baseball field. Like, it's just like baseball, 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 baseball. They're like, yeah. At least the part we flew over, I don't know. It may just be, you know, my pilot took a stereotypical path. I don't know, but okay, I digress. So we have two inner automorphisms, phi G and phi H, and you compose them. And when you compose them, check it out. You got conjugation by GH again. This, by the way, is also the proof of, as it happens, you know, if you think about it, what we're looking at right here is the proof of axiom 2 for the group action by conjugation. Because this is G, this is like, I mean, this right here is literally, I want to say it's G star H star X, basically, and this shows that that's the same as GH star X, if you sort through it. Anyway, so we have shown that the composite of inner automorphisms is an inner automorphism. And then, since I'm not being optimal in my efficiency, I then show that the inverse conjugation is inverse to the conjugation, right? And I didn't go to the trouble of showing that in detail, but it's also true. I mean, once you've shown this for arbitrary G, this follows immediately anyway. But therefore, the inverse is the conjugation by the inverse, and by the two-step subgroup test, we found that the inner automorphisms are a subgroup of the so-called automorphisms. I think if an automorphism is, if you have an automorphism which is not an inner automorphism, it's called it is in fact called an outer automorphism. Very good. You got it. This solution is going to hurt us a little bit to look at, I will tell you. You know how sometimes like I help you guys, but then after I think about it for a while, something clicks? I think this is one of those. So problem 42, what was the statement of the problem? Dang it. I think I was supposed to calculate the inner automorphisms of D4. I think that's what the problem says. It says calculate the inner automorphisms of D4. It's a little bit vague what that means. Yeah, so what I should have said is, right, what I should have said is determine the distinct inner automorphisms of D4, then find their Cayley table. To make it more interesting, what is it isomorphic to? Right, in a future year, that's how I should reformulate this problem. Anyway, so that is hopefully irrelevant to you. Or yeah, it could be a test question, that's true. That is how I roll, isn't it? Let's see here. So the center, or z-center, of D4 is 1 in x squared. I stand by that pun. Which means that x squared z is equal to zx squared for all z, right? When you're calculating the inner automorphisms of something, to determine the unique ones, if you know what the center is of the group, it guides your calculation. We were not paying enough attention to that when we talked about this previously.
Yeah.
So if I look at phi g, Fiji of z, well that's g inverse z g inverse, but that's x to the fourth because that's 1, right? And so that's x squared g z g inverse x squared. I moved the x squared over there because x squared commutes with everything. So it's cool. It's cool. X squared is its own inverse, so sock shoes is shoes. No, it's socks shoes. Sock shoes is equal to shoes socks in this case, I guess. No, I don't know what that's not the right analogy. But anyway, this is true. And so voila, the phi g is equal to phi x squared g, and that's for arbitrary g. So I don't need to go through it over and over and over again. I can just okay, that's how it works, you know? And so it suffices to look at this one, this one, this one, and this one, because everything else is obtained by multiplication by x squared. Like phi x squared, phi x cubed, phi x squared y, and phi of x cubed y. That's everything. Moreover, if we paid attention to the previous problem, like I should have, and that was not in my mind when I talked to you guys before also, there's another efficiency, which is that to multiply these, I just multiply their conjugates, right? Because remember, this is the formula we proved in the previous problem, which is to say that the composition of the conjugating maps is the conjugating map of the product of the things that are conjugating, just like that, you know. So, you know, that's how I found these products. I did not find them by evaluating these on all of D4. I mean, I found a slick way to evaluate on all of D4 when I talked to you guys, which was saving us some labor, but let's face it, this is a way better way to think about it.
This is when we computed all the, okay.
Yeah, I spent a long time on this problem, and then as I was starting to write it up, I'm like, no, I'm not doing this the right way. I should think of it this way. It's way, way faster. But I had to do it the other way in order to just see past it. I mean, I don't know. Okay, now if you look at this, 1, 2, 3, 4 things squared to the identity. In particular, these are non-identity things which go to the identity. That's the Klein 4 group because it has 3 elements of order 2. So it's got to be isomorphic to Z2 cross Z2. Es bueno, and here is shout out to the wrong way to do it. And also, I would point out that my new way to do it gives us insight into how to do other problems like this, which are, from the old way of thinking, unreachable. Okay. Galilean number 30. I forgot about this problem. What is this? Suppose G is finite, abelian group with no element of order 2. Shows that the mapping G maps to G squared is an automorphism of G. Show by example that if G is infinite, then G maps to G squared need not be an automorphism. Oh, finite, yeah. Okay, so we consider the map phi of G equals to G squared. Notice the word abelian, very important. So phi of GH is GH squared, which is GH, which is G squared H squared, which is to say, oops, I forgot to write something here. That is phi of G times phi of H. Therefore, oh, I have it here. Phi of GH is that, so phi is a homomorphism. And then I need to show that it's a bijection. So the kernel is this, but that is just the identity because we're given that there is no element of order 2 except for, well, there's no element of order 2. So that's just the identity, which shows that it's a bijection. And in the case that, oh, this is a mapping from G to G, right?
Yeah,
So I've just shown that it's injective. Therefore, it's surjective because G is finite.
okay, that does follow?
Yeah.
I was thinking that would follow. But
That was problem 10 in a previous chapter. We proved that back in another...
I was like, we had a previous chapter assignment that had 10 problems? Oh, wait, you mean, okay.
Let me see if I can find that really quick. Just give me a second here. See? There was a point to these. Now you can appreciate it. Check this out. Conjugation by sigma. is doing what? Tau's got 1, 2, 4. What's tau have? It's got 1, 5, 4, 2, 1, 5, 2, 4, right? That's tau's disjoint. I mean, that's its proper factorization, all right? And so what happens when you conjugate by sigma? Same numbers. To what? Oh, man. Come on. Oh, man. Oh, man. Oh, man. This might be wrong. That is probably wrong.
Well,
This 3 does not belong. It should have 1, 5, 4, 2. 1, 5, 2, 4. I've got a 1, I got a 5, a 4. This 3 does not belong. Let me think about that. 4 goes to what? 4 goes to 5. 5 goes to 2. 2 goes to 3. Oh, man. Son of a gun. Oh, pretend this didn't happen. I'll have to go look at this again. Conjugation shouldn't change the numbers in the cycle. It should just permute them. Scramble them, yeah. Because, well, if you take a hard look at the thing we were doing last class with the group action, anyway, maybe tomorrow it'll come up. Here it is, problem 31, Galilean number 10, page 12, page 112. Suppose S is a finite set. You have a function from a set to a set, which is 1 to 1, if and only if it's onto.
okay.
There it is. G is a finite set. We're using that. Yeah, I threw that in the homework because it's important.
Yeah.
Where were we? Ah,
Because I was wanting to use that, but like, just kind of intuitively, but I couldn't remember.
that is something that you have, I hope, proved in Math 200. Goodness gracious.
Yeah, probably.
I mean,
That's a long time ago.
Okay, so all right, so we've got a bijection, right? Now here's the counterexample. If we look at an abelian group about this additive group integers, right? G goes to G squared is the map G goes to 2G in additive notation. And of course the image is the even integers, and so it's not surjective. And
We're just finding a counterexample.
yeah.
In that case.
Infinite case, yeah. So just the times 2 map and the integers work. I'm sure there are other examples. Problem 33. In retrospect, it would have been nicer to make this problem 42 and make problem 42 problem 43 or something, because this is part of, although I did not do this, I wrote the solution down to 42 before I saw this. And then when I saw this, I was like, oh, dang it. So if a student had actually done the totality of this homework and got stuck in 42 and done this, it might have unlocked it for them in principle. But anyway, here it is. Prove that if you have, suppose G and H induce the same inner automorphism, prove that H inverse times G is an element of the center. So if they induce the same automorphism, that means inner automorphism, they're both equal for all x, which means this. Multiplication. This is way, way too complicated, guys. Don't waste your time thinking about this. Just go from here and, you know,
H by G.
right, yeah.
By H inverse.
Exactly, exactly. Which is what I eventually get around to down here. More to the point. I just didn't feel like erasing that because, you know, I'm lazy. So yeah, like you said, right multiplication by G, left multiplication by H inverse, and bam, you've got that. which shows you that this element commutes with everything in the group, consequently it's in the center. Brings us to 12. Here we have, what were we supposed to do? We're supposed to find the left cosets of 1, 11, and U30. I mean, there's nothing really, I mean, this is just a straight calculation, right? So, I mean, one thing that's helpful is the property of the Euler phi function, the multiplicativity, these relatively prime 6 and 5. So there's 8 things, like I know that, that's helpful. And if this is a subgroup of order 2, that means I'm looking for 4 cosets, one of which is H itself. And so like I got 7H, 13H, 19H, which can be rewritten as 17H, 23H, 29H. And so here's your factor. Well, here's your set of cosets. It may or may not be. Well, you guys tell me. Is that a factor group? Is H normal? Because the G mod H is only a legitimate factor group if H is a normal subgroup. We proved that the coset multiplication only makes sense in such a context. It is. Yeah, because it's an abelian group. So abelian groups in an abelian group, all subgroups are normal. The left and right cosets match, whether it's a multiplicative or an additive abelian group. In this case, it's a multiplicative one because it's in the group of units. Yeah. Prove the following isomorphisms. Oh, yeah. So here we go. U7, Z6. Right. So what I did was I noticed that these are both cyclic groups of order 6. This is generated by 3. So being that they're both cyclic groups of order 6, that means they're isomorphic.
Oh, you can just say that?
Yeah. Yeah. And here's the proof if you forgot. I mean, here's self-contained proof.
Right.
If we have 2 cyclic groups of order k, then the isomorphism is this. And the details to that are in my example 2.21, page 67. But yes, if you find that 2 groups are cyclic groups of order 10, respectively, they're isomorphic. Yeah. Because of that example and this isomorphism. Right? We don't have to reinvent the wheel for every time we find a pair of cyclic groups of order such and so forth. Of course, you could also write the Cayley tables, which I do here. I'm giving 2 solutions. So like here's the Cayley table. And this is an example where I was talking about, this is also interesting because in order to make the Cayley table match up, I had to put them in a non-standard order, see?
Yeah.
And I forgot to put the number back in here because I whited it out. I whited it out and then I forgot to put the number back because I wrote the wrong number there and I forgot to fix it. Oh well. I guess it will forever perplex students. Sad but true. All right, so it's kind of fun though. Like 2 goes to 2 and 5 goes to 5, but and 4 goes to 4. Like, but the meaning, like the 3 becomes the 1, and the 6 becomes Mm-hmm.
And he has a bunch of different Cayley tables, but one of them he, like to show the mapping, he put like both values in the second Cayley table to like show, you know, like this multiplies to this, but that corresponds to this element. And, you know, and he did that just so that it was a little clearer, you know, and he had it in different colors. But it was just kind of cool to look in his book to see like the mapping of the different objects.
Yeah. So I don't know. I mean, how do you decide how to reorder the elements? Just I don't know. I look at it and I look for the order of things and any kind of clear patterns, and you know. But anyway, that's the natural isomorphism here: 1 to 0, 3 to 1, 2 to 2, 6 to 3, 4 to 4, and 5 to 5. And the fact that that's an isomorphism is revealed by the fact that the Cayley tables look the same. But I much prefer the argument that these are both cyclic groups of order 6, as it is by far more efficient. Here, we have an infinite group, right? And so we're supposed to show that's isomorphic to the rationals. Goodness, I think it's pretty obvious that you want to do psi of n equals to that. I mean, I don't know what else you would do. So that's pretty much the only thing to try. And then this, and you notice here, this is unqualified, unadorned, right? So we're talking about additive. Because if we're talking about multiplicative, we'd have to throw out 0. At least for now. After we put a ring on it, then, you know, other things happen. But for the moment, we're groupists. So we're not rings by spring, rings by Halloween. It's okay. So yes, additive. So I'm going from an additive group to a multiplicative group as it happens. So, excuse me, phi of n plus n is this, but unmultiplying them is this, which gives me that, so it's a homomorphism. And then you can prove it's, onto is easy, 1-to-1. I chose to actually not calculate the kernel for once in my life. I just set them equal and showed you get A equals B. You can still do that. Like, you don't have to calculate the kernel if you don't want to. It gives me joy to calculate the kernel because it confuses students, and that's my goal. So mission accomplished, right? All right, so 47, what are we supposed to do here? I think we're supposed to show these are not isomorphic, right? Now this one is wonderful because here we have a finite group. It's got a lot of things in it, 625, right? Because you've got 4 spots to fill, and each one has 5 possibilities, and there's no limitations in this, so it's just 2 by 2 matrices from 5 times 5 times 5 times 5? 25 times 25 is 625. No. It's just a 2 by 2 matrix with elements from Z5, so I think it's 625 distinct choices, which is a lot, but it's also not infinite. So this is an infinite group. For example, if you don't believe me, any scalar multiple, non-zero scalar multiple of the identity is in there. So that's obviously infinite, right? Because C can be any non-zero real number. No bijection is possible, so it's not isomorphic. So size of group is the first and most obvious thing to check. By and large, all of the examples we ask you have the same size, so it doesn't tend to pay off much. But man, when it pays off, it really pays off. So Z20, Z22, 222, and the dihedral group of order 222, otherwise known as D1111. Wait a minute, 111. Of course, this is a cyclic group, and this is not. So I need to go into a little bit of detail there, though I shouldn't just say that. So of course, this is generated by 1, whereas, I guess I did just say that. Fine. Yeah, that's a good. Why am I talking myself out of that? It's obvious that D111 is not cyclic, so they're not isomorphic. But another way to be more explicit, you can count the number of elements of order 2. In particular, all you got to do is point out that D111 has xy and x squared y. I don't know why I didn't use y. I could have used y, like y and xy, right? Both element order 2, but we know from the study of cyclic groups that a cyclic group can have at most 1 element of order 2. Otherwise, it would have more than 1 cyclic subgroup of order 2, which would violate what?
What is next?
Our fundamental theorem of cyclic groups. Now, A4 is not isomorphic to D6y. Oh, this one's a little bit trickier. So A4 has got 12 things in it. D6 has got 12 things into it. Man, that doesn't help. Here is A4 explicitly. Even permutations, right? Notice that this has 8 elements of order 3. How do I find the elements of order 3? 3 cycles. One of them, 2, 3, 4, 5, 6, 7, 8. In contrast, D6 has like no element of order 3, and that's what I'm arguing here. These are elements of order 2, that's order 2. This is order 6, that's order 6. This is order, wait a minute, oh that's order 3, isn't it? So I think x squared and x to the 4th are both order 3. So there are 2 elements of order 3, not 8 elements of order 3. Consequently, it cannot be isomorphic. You pick whatever order you want to. You could pick on elements of order 2 or 5 for that matter, right? That's the most obvious thing to do. I'm an idiot. No, 6. I should have picked on, well, elements of order 6 is an easier argument, right? There is no element of order 6 in here. So therefore, but this has an element of order 6. Neither of them are cyclic. This has no element of order 6. This has an element of order 6. Not isomorphic. That's a faster argument. You don't have to enumerate the elements of order 3, but I'm just, you know. Okay, so like a multiplicative group of reals, multiplicative group of complex. The critical thing about complex is you got that I squared is minus 1, I to the 4th is 1. So check it out. Psi of I squared is psi of II, which is psi I, which is psi minus 1. Psi 1 is psi minus 1, which is 1. So check it out, yo. Psi of minus 1 squared is equal to 1, which is to say that this is just real garden variety algebra. If you've got something squared equals to 1 and it's a real number, solutions are plus or minus 1, right? You can complete the square and factor and use the cancellation property for real numbers if you think that makes it more correct. Anyway, solutions are plus or minus 1. And so psi of minus 1 is a real number. And notice that psi of 1 is not equal to 1 because psi of 1 is 1. And psi is an injection. Right? So psi of minus 1 has to be minus 1. This has to be shown. This cannot be assumed. There is logic that has to be supplied to prove this. Just supposing you can pull minus 1 out is not legit because this is not, we have the homomorphism property is this. It's not that minus 1 pulls out. This is not a linear transformation. I can't just pull minus 1 out. I had to earn this. All right? Yeah. And so then if you look at this, psi of I squared is psi of minus 1 is minus 1. That shows that psi of I squared is equal to minus 1. Oops, no such solution, no such psi of I exists in the reals. You can't have something squared equal to minus 1 in the reals. Consequently, no bijection can exist because we get an impossible equation. Now, the other way to do this, the way I expected you guys to do this, was just to use the theorem I proved in the notes, which said that the solution sets for isomorphic algebras have to be the same for an equation. So if you look at x squared equals to 1, or x squared equal to minus to 1, and compare it in the complexes versus the reals, the fact that those have different solutions forces the group of non-zero numbers, non-zero reals and non-zero complexes to be not isomorphic. Because we have that equation thing is easier to use than this. This is, I wanted to do direct combat. But you could use the equation theorem. That would be, I think, easier. And this is our last problem for today. This problem I assigned you guys because I thought it would be nice to have something that's sort of about rational numbers and structure of rational numbers. And it took me a while to figure this dumb problem out. I wonder if any of you got it. I don't know, maybe the solution's online somewhere? I don't know. I don't know. Let me walk you through it. It's a little bit sneaky. So we're supposed to prove that the group of additive rational numbers is not isomorphic to any proper subgroup of Q. There's actually dozens of questions like this about proper subgroups of infinite groups. These are tricky questions. There's a whole family of these things waiting for you when you least expect it. Sorry. So P over Q, a rational number, is 1 over Q plus 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 1 over Q, P times, right? All right. So if it's negative, let's assume we're working with a positive rational number. If it was negative, we could subtract it p full times, all right? Minus p full times. P is negative. All right, so identity. This is equal to that, right? So that means by the homomorphism property, additive homomorphism, I can pull out the p. This is the homomorphism property. We have phi of a to the n, phi of g to the n is equal to phi of g to the n. In additive notation, that's phi of na is equal to n times phi of a. This is just that identity in additive notation in the specific context that we're interested in here. So I have that, right? But now this. I'm assuming, of course, that we have a isomorphism from Q, from the rationals to a proper subgroup. Okay, and I'm looking for a contradiction. That's how all of these stupid problems are done. They're all contradiction problems. That's probably why a certain professor loves them. I won't name names. Let's see here. I assume. I don't know. I actually don't have any direct proof of that, but I believe that. Funny. So now here's the thing that I had to search for this, and finally I found somebody who did this, and I'm like, oh, that thing. Because I've done this before. I just forgot about this stupid trick. So 1 is Q over Q. So that I can rewrite as Q times 1 over Q, which is psi of 1 over Q plus 1 over Q plus 1 over Q plus 1 over Q plus 1 over Q, Q full times, right? Which is not equal to psi of 1 over Q. There's a Q missing here. Mission critical Q missing here. As you can see, it's reappeared down here. It was in stealth mode up here. Sort of active camouflage, perhaps. Psi of 1 over Q is equal to 1 over Q times psi of 1 then. Yay! So we have earned, see, now we have earned the right to pull Q out.
Yes.
Okay.
And so now we have that psi of P over Q is equal to P over Q times psi of 1. All right, great. Or, more to the point, psi of x is equal to x times psi of 1 for an isomorphism from the rational numbers to a proper subset of the rational numbers. All right, this is still not done. All right, so if H is a subset of the rationals and it's not 0, right? It was a non-trivial subset. And it's not equal to the rational numbers, what does that mean? That means that there is some Z in Q which is not in H. The fact that H is non-zero means that this, and that this is an isomorphism means that there's some Y in H and some X in Q which has psi of X equals to Y. It was important to know that that's where I needed the non-triviality of H. That was important here. That gives me the existence of this Y. And the fact that psi is an isomorphism means that some X maps to it. So psi of X is equal to X times psi of 1 by our identity is equal to Y. In other words, psi of 1 is Y over X. All right, I can rewrite psi of 1 as Y over X. Then, if you look at psi of Zx over Y, I can pull out Zx over Y times psi of 1, right? But that's Zx over Y times Y over X. So Y's are canceling, the X's are canceling, and it leaves us with Z. So psi of this is equal to Z. Everything in psi is supposed to map to H. We just map to the thing which is not in H. Oopsie. So apparently the mapping is not into H. That's a contradiction. That's a clear contradiction. Consequently, no such map exists. Consequently, no proper subgroup, no non-trivial proper subgroup of the rational numbers under addition can be isomorphic to the rational numbers under addition. There you go. This is not something I came by lightly. I had to think about this for a while. This right here finally dawned on me, like I finally had a spark of inspiration, and I was like, oh, whoa, that's what I'm supposed to do. I knew I had to pick the Z which is not in H and use that. And I knew I had to pick the point that mapped to the point and use that. So once I had all that, and once I had internalized the point of this identity, I found this very early on somewhere. Somebody's like, "Oh, this it's immediately true because any isomorphism is of the form x times psi of 1, so it's clear." No, it's not. It's not entirely clear. This is not entirely clear. This is some steps later. And I'm always like tired, and so when somebody says it's entirely clear and I don't see it immediately, I'm like, is it me? Is it clear? I don't know. Anyway, what's clear is we are done looking at the solutions of homeworks 10, 11, and 12. Next time we'll pick up with 13 and 14 and whatever else I got done. Thanks, guys. I guess I got to go turn it off. I have posted up through 14 now.
Okay.
Yeah. I can't post further than that for reasons which are obvious.
Yeah.